Okay, thank you everyone. Thank you for waiting and good afternoon. Hope you had a good lunch. Really happy that you can join us for this session, Uber's Innovation in OpenSearch for a Cloud Native Future. So I'm Pallavi Priyadarshini and I lead engineering for search security releases at OpenSearch project and the Amazon OpenSearch service. I'm also a member of the technical steering committee of the OpenSearch project. And today I'm thrilled to introduce to you Charu Jain, who is an engineering manager at Uber, and she leads search and the real-time data platform out of India. Uber is a valued member of the OpenSearch Software Foundation, and they are making significant contributions to the future of the OpenSearch project, and we will walk you through some of that. So I'll begin by sharing some highlights on the OpenSearch journey, just for a quick recap. Then I will cover what is the current OpenSearch architecture in open source, and then I will kind of briefly cover what is the future cloud native architecture we are marching towards. And then Charu will come in and she will share Uber's perspective on the kind of use cases that necessitate a cloud native architecture and the key areas where Uber is making code contributions to OpenSearch. So most of you are aware, but just a quick recap, OpenSearch is a trusted open source search and analytics software. And obviously we already covered in the keynote, it was transferred to the Linux Foundation in September 2024. And we have 16 members in the OpenSearch Software Foundation. And the reason I show this, like Uber is one of the members as well. And the foundation has a technical steering committee that has 11 participating organizations. And one of the responsibilities of the technical steering committee is to make sure the project is headed in the right direction, right? So we have a public roadmap. You know, that is one of the goals of moving OpenSearch to the OpenSearch Software Foundation is we don't want it to be a vendor neutral, we don't want it to be a vendor controlled community, right? So that's where it has really taken off after the Linux Foundation move. And our partners such as Uber, they are running large scale workloads on OpenSearch and planning to move more workloads to OpenSearch. And they're pushing the boundaries of scale, performance, operational simplicity, and much more. And that's where contributions from them to make OpenSearch scale better, faster is very, very valuable. So this is kind of the current architecture. Most of you are familiar, but I'm just going to show you a little bit. This is the current architecture. OpenSearch is a distributed engine built on Lucene. And today it looks like this. When we started out, it's mostly tailored towards on-prem and cluster-based deployment. And I'm talking about the open source OpenSearch, right? So as you can see, we have the concept of data nodes, and the data nodes serve writing as well as reading, meaning they can be a searcher or an indexer. They serve dual roles. Then metadata or cluster manager is a monolith today, and it needs to be propagated to all the nodes. And that's where it becomes harder to manage large scale deployments and also scale on demand, right? Today in open source, we have already moved to a remote store architecture, and I can see like the contributors, you know, from this region, like from India, were very active in moving it to a remote store based architecture. So we have remote store, but the searches are still served from local disks. So during ingestion, the segments get uploaded to the remote store, but your searches are still served from local disks. So this is where we want to move towards, right? more cloud native architecture, which is stateless. So with this architecture, the writers, we have reader-writer separation, and the writers will pull data from event stream. So we want to move to a pull-based model, and they will upload the data to your remote store, and then the readers on the search path, they will download data from the remote object store. Then metadata also will be moved to the remote store. It's already moved to the remote store today, but we do want to break it down into smaller components so that each component just downloads whatever metadata it needs. We want to move away from the monolithic cluster state, right? So there are certain areas where active work is going on already in open source to move towards a cloud native architecture. So obviously having a remote store based architecture allows us to decouple components. So we want to make sure that each component kind of scales independently, and it can scale up and down on demand. With local store, scale in and scale outs are harder as it involves a lot of data movement, and we want to move away from that. Then even on cluster manager, like I mentioned, we already have a remote object store based cluster state. However, we want to divide it into smaller, like split it into smaller logical and physical partitions. I kind of already covered with the reader-writer separation, the indexing and search workloads can have better isolation and they can scale independently. And as we are separating out components for a cloud native architecture, we want to make sure that the communication between them is more efficient, right? So that's why we are taking steps towards moving towards a more performant alternative to our today's REST APIs. So we are introducing protobuf and gRPC, and gRPC with protobuf as the message format makes data transmission more efficient across nodes and between client and server as well. And then last but not the least, the pull-based ingestion, right, will make sure that your producers of data and the consumer, OpenSearch, are kind of decoupled. Like today, if the ingestion traffic is spiky, OpenSearch starts kicking in with its back pressure mechanisms, right? So with pull-based ingestion, you can make sure that you can scale up your ingesters on demand, right? And plus you have these queues, you can implement priority, you can do a lot more than today's push-based model. So we are very happy that a lot of this contribution is coming from Uber, which Charu will go through in detail. But I do want to say that basic versions of all of these went into OpenSearch 3.0, which was released 1 month ago, right? So OpenSearch 3.0 was a milestone release in moving towards a cloud native architecture. And we will continue expanding on building some of these features in the 3.x line. And I do want to thank the contributors. I can see several of you who are helping us along with Uber to move towards this architecture to make sure like OpenSearch long-term architecture is scalable. So with that, I hand over to Charu to continue the Uber segment.
Cool. Thanks, Pallavi, for the introduction. Good afternoon, everyone. My name is Charu, and I will be talking about the Uber search journey in the last 2 to 3 years. So first, I'm going to talk about few of our use cases which are business critical and we are operating at a very high scale. Then I'll cover our old architecture, the new architecture, our journey, and then how we are converging this to the OpenSearch. So the first use case is Uber Eats. Unfortunately, this is not operating in India anymore, but very popular globally. So there are millions of restaurants on Eats, and every restaurant has dishes. So search at this scale becomes a very complex problem, because it's not just about a reverse index lookup, but you have contextual search, personalized search, and there are a lot of variables in play in order to make the complex decision making. We will also do a case study of this use case in the later slides, but yeah, another thing is Eats is also now, we have grocery in the Uber Eats app. So the scale has been increased by many folds, and the same architecture has been able to scale up, live up to that scale. Next is the classic maps use case. I'm sure everybody who has used Uber rider app is aware of these screens. So maps is used for our rider app, our driver app, and these are the three different screens where I'm trying to highlight the kind of search that we support. Again, we have a huge location index where all the location entities are indexed. We provide lexical search, which is most commonly used for doing your regular search, which also incorporates the personalization, like you may add a star to your favorite places, and also it takes into account where you are currently, the sharding, which location you are currently part of. Then with the semantic journey, like as we have introduced the vector search use cases, we also support semantic search in our Maps app. Meaning now if you search for like a burger, maybe a Burger King or McDonald's will also come into your result. And then the third screen is your pin drop search, which is after your ride is booked. So suppose you're in this hall and you're trying to book a ride, you will probably be routed to the nearest pickup point, right, which is outside this hotel. So that pickup location is also powered by search. We index the road segments in our index, and then the most optimal segment is returned when your trip is booked. The first two use cases were example of near real-time search, meaning you can live for minutes of freshness, but they're also very critical in terms of latency. But the third use case which I'm talking about is the rides use case, which is very, very critical. So even for matching, when you're trying to book a ride, matching the rider to the driver is also powered by search. So there is a complex matching algorithm in place, but the initial set of candidates are powered by our search infra. Here, freshness is of key essence because we cannot tolerate even single second digit of freshness. The driver location is indexed every in the order of ones of seconds. So this is another critical use case which is powered by the search platform at Uber. And then the last use case is the most important now, the RAG and GenAI use case. So our customer support experience has improved a lot, right, in the last few years. Like imagine having customer support maybe 5 years ago, we probably used to go over a phone or were chatting with a human behind the scene, and the experience was not as fast or smooth because you're waiting for a human to like sort of answer your queries. But now with the bot and then the intelligence on the bot, we have powerful LLM models, and it has become very efficient for companies to sort of build their bots using the RAG and GenAI, which not only improves the user experience but also saves a lot of money because you don't have to hire humans for doing the same job. So I'll quickly give an overview of search platform at Uber, which has gone through a journey of its own. So for the sake of simplicity, call it old search, which was there, which is where we started from. So we have started with our own in-house search engine, which is powered by Apache Lucene. We have the Lambda architecture for ingestion, meaning we have offline index build job, for which we use Spark for building the offline index. And we also have real-time ingestion, for which we are using Kafka. So real-time use cases will consume from the stream of updates on real-time basis and continuously build your index. So your index is sort of offline, a combination of offline and online updates. We also support priority-aware ingestion in the streaming ingestion. We have more advanced sharding technologies like geo-sharding, because for the use cases which we talked about, the maps and the Eats use case, sharding is like when you shard with a latitude sharder, it becomes more optimal and more optimized, like you'll be able to index your location, your entities more locally. Also, we have worked on the index layout and query operators for more efficient performance of our query. So some of the things, like we do some offline ranking when we are building our offline index. For example, like if your dishes are more popular, they will be ranked higher in the index, and then we can leverage query operators like early termination for faster results and improved latencies. So now we can do a case study of our delivery use case. By delivery, I mean eats and grocery. So on the Eats app, there are two entry mode for a user. When you open the app, you are served with the feed, which is a scrollable feed, and it is pre-populated with some groupings. So it is curated based on your past history, your personalization, location, what is trending and whatnot. And the other entry point is your search bar, where you can directly search for a restaurant or a dish or a grocery item, etc. So I want to emphasize again, like when the data is huge, when you have so many choices, the decision making is complex. So search is kind of solving that complex decision making for you by doing better ranking and better returning of the search results. Cool. So this is like a basic query that is powering your delivery search. So think of a use case where I'm trying to search for milk in the search bar. We have, so how we are indexing in our indexes, there are stores and there are items. So by stores, I mean stores like Target, Costco, and then items, there can be millions of items. So there can be small stores, there can be big stores with millions of documents. And then when we run this join, we are trying to do a join between the item and the store. And like I talked about, we are doing partitioning on the latitude or location. We will put a filter on the location, which is the hex ID, H1, H2, and we'll search for the query which is milk, and then we'll do the group by. Now group by is done for bringing diversity to our results. So for example, if I'm searching for milk, I don't want all the 10 results from one store. Hence we do a group by so that we can sort of put a limit on every store and give a more diverse set of results to our users. Now this query is pretty standard and will work for a small scale kind of a use case, but with huge amount of items and stores, this becomes more unoptimized. And in order to optimize, it is important how you can sort of store your documents. So here we are first storing the store and then all the items to that store, and then the store too, and then all the items, and so on. So we can do two kind of joins here. So Lucene provides two type of joins. One is your query time join, which is more during the runtime, and it can be more expensive. The other way to do is by doing the block join. But for doing the block join, we have to leverage this kind of layout which I talked about. We will first store or index the store, and then all the items of the store, and then the second store and all the items of the store, and so on. Yeah. So assuming block join assumes that your data is pre-sorted, and then you can run that query efficiently. So so here the same thing, when you do your data in this kind of a layout, you can have pointers, and then you can traverse the same index more efficiently, because this is more like a skip list, and then you can skip there is an all parent iterator, there are eligible parent, for example, if you filter on the parent, for example, if you're trying for only vegan restaurants or only some sort of particular store, and then you can also have child iterators. In this case, this is the milk part. So this way you will be able to hop and iterate over this very, very fast. Now this is very ideal, but when in the real time you have constant updates, constant inflow of updates, deletes and whatnot, this becomes challenging, because sorting something in memory can now affect your query. Sorting is very CPU intensive. So that's why it requires a read-write separation. And that's what I think Pallavi initially talked about, and I'll also talk more in the next slide. So read-write separation becomes more evident why we need it. Again, with this kind of an architecture, we can like fast forward for early termination, and the extension here means the same layout can be used for both eats as well as the grocery kind of use case. So this is the more revamped or the new architecture of Uber internal platform. We have separated the ingester, which is the write component, and the searcher, which is the query component. We are heavily using Kafka for the streaming ingestion. We have a gateway, which is more like a aggregator or a federator, which routes the read and write traffic to the relevant components. And we have the ingester node, which continuously consumes from Kafka. They do the more expensive operation, which is like the sorting, the putting it in the right place, generating the segments, and then uploading it to the remote storage. And then the searcher node can download the relevant segments and then serve the query traffic. And we also have the offline build, which is for mostly for doing backfill or doing bootstrapping for a new use case, which can build your offline index and then also upload to the same remote storage. So this way we have achieved the read-write isolation, and both can be independently scaled depending on the QPS. So on the days like if the read QPS is very, very high, like for example there is some festival or something is trending, you can scale your searcher nodes. Similarly, if there is more write traffic, like a new store is getting onboarded, which has several millions of documents, you can add sources on the ingest side, and both can ingest independently. Another thing is searcher is mostly the user facing, so it is very important that you keep the CPU utilization low for your searcher component, and whereas ingester is mostly doing an behind the scenes, so you can sort of use more CPU on the ingester component. So Project Sunrise is the path forward. Now that we have solved our problem in the Uber ecosystem, why we want to go to this model, right? So Project Sunrise is something which was coined about a year ago within Uber, which is mostly in the direction of collaborating with the open source community to build more sustainable ecosystem and foster innovation. So what I've talked about is just one problem which we have solved, but there are so many problems that we still need to solve. And when you join hand with the open source community, some of the things are already out there, out of the box, and you can like leverage it. So it's for faster innovation, like faster iteration, and like you can try out things, also contribute it back, and you kind of get best of both the worlds. So the product, we can get benefits on the product features, but in addition to that, in the open source, there are also rich toolings like debugging toolings, observability, dashboard, security, etc., which can also be like leveraged by the Uber teams. So that's the way forward that we will continue to collaborate. So Uber and OpenSearch. So last year, Uber joined OpenSearch Software Foundation as a founding member, and we have jointly authored OpenSearch 2025 roadmap, which I think Pallavi also talked in her initial slides. Now next, I will talk about some innovations that we have already started contributing, and they are available in the OpenSearch 3.0 version in experimental form. So pull-based ingestion is one of the things that is now available in the experimental mode. This is about ingesting, like our search nodes can start ingesting data from Kafka. Kafka is very heavily used in the Uber ecosystem. With Kafka, you can sort of control the ingestion traffic. It smooths the ingestion spike. And again, this is helping us achieve the same read-write flow. How in Uber we have set up is we have a multi-regional setup in the Uber system. So what we can do is like there are regional Kafka topics where the updates are coming, and then we have aggregated Kafka topics which sort of aggregates the updates from the regional Kafka topic, and then your regional OpenSearch node can continuously consume from the aggregated Kafka. This way we are able to solve the problem of cross-region replication without actually doing the cross-region replication, because you're consuming the events from both the regions. With Kafka, the other advantage is Kafka has already solved a lot of problems in the Kafka ecosystem, which is around durability. There is offset management. We can replay messages very fast and also recover them as there is some storage there. So even in the case of like there is huge traffic spike, or if you want to like sort of, if you miss some updates, you want to replay, or you want to sort of skip some updates and start consuming from a future offset, all of that is possible with the with this kind of a setup. And within Uber, we have other platform teams like Pinot, Flink, who are also sort of leveraging the similar architecture. So this slide talks about the pull-based ingestion architecture, which is now contributed. So I'm giving like a very high-level thing. There are these search nodes, and we have a ingestion engine which is like continuously pulling from any streaming source. So for now, the Kafka and Kinesis support is there, but in future we can even make it more pluggable, like there can be any other streaming ingestion source. And then we are storing the metadata in our index data, like the offset around the index. So in the slide, the RFC for this is linked, which has more details around this design. And this is how you can configure. So in the settings, you can sort of define your ingestion source, and you can define your topic name, your host name, etc. And I would encourage everybody to sort of try it out, and like I said, this is experimental, so try it out and let us know how your experience is and what can be improved. What is planned immediately after this is the priority aware ingestion. So we can basically, this is something which is work in progress, but the whole idea is that you can sort of consume multiple Kafka topics and give priority to any topic. So this is very helpful for use cases. So for example, if a new store is getting onboarded, which is not critical, and it shouldn't sort of overwhelm the regular updates. So you can sort of distribute your ingestion into multiple Kafka topics and give priority, like which updates are more critical for your use case. Another example is like if you want to backfill your data, you can also use another Kafka topic with a lower priority and do the same job. Another feature which is contributed by Uber is the gRPC protobuf support. So at Uber already gRPC is the norm, like all our microservices communicate with the gRPC and protobuf protocol. And with this contribution in the OpenSearch, we did our benchmark and observed that it's already more efficient and faster in terms of query performance. It is strong, there is strong typing which is coming out of the box in protobuf, and this RFC is also linked in the slide, so please look at it for more details. And the other things that we want to contribute, this is the upcoming work planned for the next 6 months or 1 year, is towards building a more cloud native OpenSearch. By cloud native, I mean something which can work at a very, very high scale. We can have like several millions of nodes in a cluster, and basically going towards a shared nothing kind of an architecture. The whole idea is the cluster metadata part, instead of storing it inside the node, it will be pulled to sort of a remote store, something like at etcd. So that is something planned. Again, with cloud native, other benefits can come like static routing, leaderless, and we can have sidecar for reader writer. The other features that we are going to contribute are things like providing a support for offline index build using Spark, the same thing like the efficient parent-child join and GPU for serving. So this is the roadmap, and we want to continue to contribute to OpenSearch and converge our architecture with the OpenSearch ecosystem. With this, I would like to end the talk, and thank you. Yeah.
Thank you, Charu. That's really insightful, and we are so excited that Uber is doing all this work. And I think the amazing thing is, as we socialize more of this cloud native architecture with our other hyperscale partners, they want to contribute as well, right? Like this morning we were talking to Atlassian folks and they want to join hands here. DTEX/IBM recently indicated they want to contribute. So I think as we get these hyperscale contributors in OpenSearch, they want the open source architecture to move towards a more cloud native stateless, and which is where we want to go in full throttle, right? So thank you so much, and if you find opportunities to contribute, all the RFCs Charu linked in the talk, look it up on OpenSearch. There are a lot of RFCs out there. We'd love to have contributions from you all as well. Thank you for your time and enjoy the rest of your evening. Okay.